Darkness between everything. There's something you think you understand, but almost certainly don't. Darkness. You've experienced it when the lights go out at night. When you close your eyes in a windowless room. You've felt that particular blackness that makes you reach for a wall. But here's the truth almost nobody confronts. The darkness you've known your entire life is a pale imitation, a sketch of the real thing. The universe contains a darkness so complete, so utterly without exception, that your brain, a remarkable organ shaped by millions of years of evolution, has no framework for processing it. It isn't simply the absence of light, it's something that functions almost like a presence, a totality that swallows the very concept of seeing. By the time we're done here, you'll understand why space is darker than anything your imagination can honestly construct. And more importantly, you'll understand what that darkness reveals about the nature of reality itself. What you think darkness is. Let's start with what's happening in your bedroom at 3 in the morning when you're certain you can't see a thing. You're wrong. You can see something, or at least your eyes are receiving something. Light seeps under the door. Street lamps push their orange glow through curtain fabric. The moon, if it's up, is bouncing sunlight off its ancient gray surface and sending it through your window. The tiny green standby light on your television is technically illuminating the room. Your pupils have dilated to their maximum aperture. The rod cells in your retina, the photoreceptors responsible for low light vision, have been adapting for roughly 10,000 to 1 million times more sensitive than they are in full daylight. You are, in the darkness of your bedroom, a remarkably sensitive light detection instrument. And your brain is doing something even more interesting. It's filling in the gaps. The visual cortex, receiving only fragments of information, constructs a complete mental image from scraps. It knows where the furniture is. It interpolates. It guesses, brilliantly and constantly, and presents you with an experience of a room rather than a genuine visual feed of one. None of this is darkness. Even in genuinely remote locations on Earth, far from any city, far from roads or buildings, you are bathed in light that your conscious mind simply ignores. The Milky Way alone deposits thousands of photons on your retina every second. The atmosphere itself glows faintly, a phenomenon called air glow, produced by chemical reactions at high altitude. Zodiacal light, created by sunlight scattering off dust particles that trail through the inner solar system, creates a subtle pyramid of illumination rising from the horizon after twilight. Even in the deepest caves, even below ground, even in environments your instincts register as completely dark, you remain on a planet wrapped in an ocean of air that traps and scatters light like a lantern made of gas. You have never been in real darkness, not once. What astronauts found. When human beings first traveled beyond the atmosphere, many of them reported being unprepared for what they saw, or rather, what they didn't see. The experience they described wasn't the darkness of looking at space from Earth, where stars jewel a black background and the mind finds the scene beautiful and somewhat familiar. The darkness they encountered was different in a way that resisted language. It wasn't the color black, it was the complete and final absence of visual information in a direction where your instincts insist there should be some.
Bruce McCandless, the first astronaut to perform an untethered spacewalk in 1984, described the experience of looking away from both the Earth and the Sun as unlike anything he had encountered in his life. He held his hand away from any reflected surface and could not see it, not dimly, not as a vague shape, not at all. His hand, which he knew to be there, which he could feel, had effectively ceased to exist as a visual object. The darkness wasn't just surrounding him, it was consuming the idea of visual reality itself. Other astronauts have described the same phenomenon in different terms, but they converge on the same strangeness. Your brain expects input. It was built over geological time to receive a constant stream of visual information and process it. Deprive it of that stream and something shifts, a kind of cognitive vertigo, an unsettling awareness that the thing you rely on most has been switched off. This happens because space is not merely empty, it is empty in a manner that exceeds any intuitive understanding of the word. The arithmetic of emptiness. Consider the air in front of your face right now. In a cubic centimeter of air, a volume roughly the size of a sugar cube, there are approximately 27 billion molecules. Write that out, 27 followed by 18 zeros. They are vibrating, colliding, carrying heat and sound. They are the medium through which you hear music and smell coffee and feel the weather change.
In the space between stars, a cubic centimeter contains, on average, about 1 atom. 1. This is not a slightly thinner version of our atmosphere. This is a different category of existence. The best vacuum chambers built by human engineers using the most advanced technology available cannot come close to replicating the emptiness that occurs naturally in interstellar space. We cannot manufacture that level of nothing. The universe produces it everywhere, routinely as its default condition. And in that emptiness, light has nothing to interact with. This is the key to understanding why space is dark despite being full of light. Photons are streaming through the void in every direction, including through the space you would occupy if you were out there. They pass through you, around you, past you. But unless a photon actually strikes your retina, it doesn't exist as far as your visual system is concerned. Light is only visible when it hits something. On Earth, you can see a flashlight beam because the light is scattering off dust particles and air molecules between you and the source. In space, there are no dust particles, no air molecules, no medium to scatter from. The beam is invisible. The light is there and simultaneously, from your perspective, nowhere at all. This creates situations that seem physically impossible until you witness them. On a spacewalk, one surface of your suit might be in full sunlight, heated to well over 100 degrees Celsius, bright enough to require heavily filtered visors to prevent permanent eye damage. Rotate slightly, and the other surface is in absolute shadow, cooling toward negative 160 degrees, invisible even if your face is inches away. Not dim, not dark gray, gone. There is no atmospheric haze to soften the transition, no scattered light to fill the shadow. The line between sunlit and dark is the sharpest boundary you will ever see, because on one side of it there is light, and on the other side there is nothing at all. Between the stars. Imagine you have been transported to the midpoint between our solar system and the nearest other star, Proxima Centauri, which sits approximately 4.2 light-years from the Sun. You are roughly 2 light-years from each of them. Both stars are visible. The Sun, which you have known your entire life as an overwhelming yellow disk that determines your sleep schedule and heats your skin and drives all weather on Earth, is now a bright star, the brightest star in your sky, but still a star, a point. It does not illuminate anything around you. It does not warm you. It does not cast a shadow. It is simply the brightest dot among other dots. In every other direction, nothing.
The word nothing is doing a lot of work there and failing at most of it. There are no surfaces, no ground, no horizon, no up or down, because those concepts require a gravitational context, and out here the gravity of any particular body is negligible. The stars, all of them, the entire sky full of them, are so distant that they provide zero functional illumination. They are data points about the universe's geography, not light sources in any useful sense. The distances involved are almost comically resistant to human comprehension. The average gap between neighboring stars in our region of the Milky Way is about 5 light-years. 1 light-year is roughly 9.5 trillion kilometers. If you compressed the distance between the Earth and the Sun into 1 centimeter, the nearest star would be over 2.5 kilometers away. And we are talking about adjacent stars, galactic neighbors. The Milky Way itself contains something between 100 billion and 400 billion stars, spread across a disk roughly 100,000 light-years in diameter. The overwhelming texture of the galaxy, if you could somehow feel it, would be emptiness. The lights are the exception. The darkness is the rule. The space between galaxies is interstellar space positively crowded compared with what lies between galaxies. Our nearest large galactic neighbor, the Andromeda Galaxy, is approximately 2.5 million light-years away. That is about 15 quintillion kilometers, 15 followed by 18 zeros. The space separating us contains matter at a density of roughly 1 atom per cubic meter. Not per cubic centimeter, as between stars, but per cubic meter, a volume the size of a large wardrobe containing a single atom. Picture yourself in a spacecraft positioned halfway between the Milky Way and Andromeda, roughly 1.25 million light-years from each. You look in one direction and see our galaxy, not the way we see it from inside, as a band of light overhead, but as an external structure, a faint spiral of accumulated starlight. You look the other way and see Andromeda, another faint spiral. Everything else, in every direction, for hundreds of thousands of light years in every direction, is absolute darkness.
The stars of our galaxy, including our own sun, are invisible as individual objects from this distance. They have merged into the dim collective glow of the galaxy's disk. Earth itself is undetectable. Every human being who has ever lived, every city ever built, every war ever fought, every piece of music ever written, all of it is contained somewhere in one of those two faint smudges hanging in an otherwise featureless black sky. And you are floating in the darkness between them, farther than any world than the mind can genuinely grasp. This is not a metaphor. This is not a dramatic framing for something more mundane. This is the actual geometric situation of the intergalactic void, experienced directly. Why dark skies are also a paradox? Here is something that puzzled astronomers for centuries. If the universe is infinite and littered with stars in every direction, then every line of sight should eventually terminate on the surface of a star. The night sky should be uniformly bright as the surface of an average star in every direction. This is sometimes called Olber's paradox, after the 19th century astronomer who gave it particular attention, though he was far from the first to notice the problem. Obviously, the sky is not blindingly bright, it's dark. So what's going on? The answer turned out to be one of the most profound discoveries in the history of science. The universe is not infinite in age. It began approximately 13.8 billion years ago in an event we call the Big Bang, and light travels at a finite speed, about 300,000 kilometers per second. This means we can only receive light from objects whose light has had time to reach us. Anything farther than 13.8 billion light-years is beyond our observational horizon. Its light simply hasn't arrived yet, and given the expanding geometry of the universe, much of it never will. Additionally, the universe is not static, it is expanding, and has been expanding since its beginning. Galaxies are not merely drifting apart through space, the space between them is stretching, like dots on the surface of an inflating balloon. The farther a galaxy is from us, the faster it appears to recede, because there is more intervening space to stretch. For the most distant galaxies we can observe, this recession is stretching their light to longer and longer wavelengths, shifting it from visible light into infrared, then microwave, then radio. The photons are still arriving, but our eyes cannot detect them. The galaxies exist. Their light is reaching us. We are simply blind to it. The darkness of the night sky is therefore not a simple absence. It is a consequence of cosmic history, the finite age of the universe, the finite speed of light, and the ongoing expansion of space. A different universe, one that had existed forever in a static state, would have a blindingly bright sky. We live in a younger, dynamic universe, and its darkness is the proof of that. The light you cannot see. When astronomers say that space is full of light, they mean something more expansive than what your eyes can register. Visible light, the entire spectrum from deep red to violet, the rainbow of colors your visual system evolved to detect, occupies less than 2% of the full electromagnetic spectrum. The spectrum runs from radio waves, which can have wavelengths measured in kilometers, all the way to gamma rays, whose wavelengths are shorter than the nucleus of an atom. Visible light is a narrow band in the middle, the window your biology happens to look through. Space is saturated with radiation at wavelengths your eyes cannot see. The cosmic microwave background, the afterglow of the Big Bang itself, light that has traveled for 13.8 billion years and stretched from its original intense heat into microwave wavelengths, fills all of space uniformly.
If you could see in microwaves, the sky would glow with a soft, even warmth from every direction simultaneously. You would be bathed in the light of creation's first moments, omnidirectional and ancient. Instead, you see nothing, because your eyes evolved on a planet where microwaves were irrelevant to survival. Infrared radiation streams from galaxies whose visible light has been entirely redshifted beyond detection. X-rays pour from collapsing stars and superheated gas near black holes. Radio waves carry signals from pulsars spinning dozens of times per second, from quasars burning with the energy of trillions of suns. Neutrinos, ghostly particles that interact with almost nothing, pass through every square centimeter of your body at a rate of roughly 65 billion per second, streaming outward from the sun and from distant stellar explosions. Gravitational waves from merging black holes ripple through the fabric of space-time itself. All of this is happening in what appears to your eyes to be empty darkness. Your experience of darkness is not a measurement, it is a limitation. The universe is not actually as quiet as it looks. You are simply not equipped to hear most of what it is saying.
The quantum darkness that isn't empty. At the smallest scales physics can currently describe, there is one more layer to the story. Even a perfect vacuum, a region of space containing no particles, no radiation, nothing at all by any ordinary measure, is not truly empty according to quantum mechanics. The laws governing the subatomic world prohibit absolute stillness. Energy cannot be defined precisely at zero, because that would require perfect knowledge of both energy and time simultaneously, which the uncertainty principle forbids. So even in the deepest void, space seethes with what physicists call quantum fluctuations, pairs of virtual particles that flicker into existence, exist for an inconceivably brief moment, far shorter than any clock could measure, and then annihilate each other back into nothing. This is not a theoretical quirk with no real consequences. The energy associated with these fluctuations, called vacuum energy or zero-point energy, is real and measurable. It is likely connected to dark energy, the mysterious force that is causing the expansion of the universe to accelerate rather than slow. The darkness is, at its foundation, a kind of boiling, activity at scales so small that every instrument we have struggles to detect it, but activity nonetheless. So, when we look into the void between galaxies and see nothing, the nothing we are seeing is not the same as absolute absence. It is absence at every scale our senses and most of our instruments can reach, layered over a substrate of quantum activity that never stops and can never stop. The darkness that looks like silence is more like a frequency too high to hear. The universe, even at its emptiest, is doing something. We just can't tell. Black holes, where darkness becomes absolute. Everything we've described so far is ordinary astronomical darkness. The darkness of empty space, the darkness of distance, the darkness of wavelengths beyond our vision. But there is a category of object in the universe that represents something genuinely different. An object where darkness is not merely the absence of detected light, but a fundamental property of the geometry of space-time itself. A black hole is a region where gravity has become so extreme that the escape velocity, the speed needed to leave, exceeds the speed of light. Since nothing can travel faster than light, nothing can escape. Not radiation, not particles, not information of any kind. The boundary of this region is called the event horizon, and it is not a surface in any material sense. It is a line on a map, a point of no return written into the structure of space itself.
What this means visually is that a black hole is not just dark, it is a perfect absorber. It reflects nothing, emits nothing from beyond its horizon, and bends the paths of photons passing near it so severely that even light traveling past at a tangent can be captured, dragged into orbit, or swallowed. If you looked directly at a black hole, you would see a circular region of pure absolute absence, not dark as a painted wall is dark, but dark as a hole in reality is dark, surrounded by the distorted, brightened images of everything behind it, whose light has been bent around it like water around a drain. In 2019, the Event Horizon Telescope, a network of radio observatories spanning the entire planet, functioning as a single Earth-sized instrument, produced the first image of a black hole's shadow, the supermassive black hole at the center of the galaxy Messier 87, some 55 million light-years away. The image showed a bright ring of superheated gas spiraling inward, and at the center, darkness. Not dimness, not a very dark region, darkness that was categorically different from the darkness around it, because it was not a place that happened to have no light in it. It was a place from which light could not escape. The interior of a black hole, beyond the event horizon, represents perhaps the only environment in the universe where darkness is genuinely complete in a physical rather than merely perceptual sense. Outside the horizon, you might find a region with no photons passing through, dark by circumstance. Inside, the geometry of space-time has been shaped by mass into a configuration where light simply cannot move outward. The darkness is structural. It is built into the rules. The cosmos, it turns out, has been dark before. Not in the way it is now, with galaxies spread across immense distances and the spaces between them empty and cold, but dark in a more complete and primordial sense. In the very earliest moments after the Big Bang, the universe was the opposite of dark. It was a dense, blazing plasma, every point in space radiating intensely, light unable to travel more than a short distance before it was absorbed and re-emitted. There were no stars yet, no structure, just heat so extreme that matter and energy were essentially the same thing. For the first 380,000 years, the universe was opaque,
a fog of energy so thick that photons couldn't move freely through it. Then something changed. The universe had been expanding and cooling since its first moment, and it finally cooled enough for electrons and protons to combine into neutral hydrogen atoms. In a cosmological instant, the fog cleared. Light that had been trapped, scattered endlessly in every direction, was suddenly free to travel. It streamed outward into a universe that was becoming transparent for the first time. That ancient light is what we now call the cosmic microwave background, the oldest light in the universe, stretched over 13.8 billion years of cosmic expansion from intense visible radiation into the faint microwave glow that permeates all of space today. After that clearing, the universe entered what astronomers call the Dark Ages, and they mean it literally. The plasma had cooled into neutral gas, hydrogen and helium drifting in vast clouds, slowly condensing under the influence of gravity. There were no stars, there were no galaxies, there were no sources of light anywhere in the observable universe. For hundreds of millions of years, the cosmos was genuinely, completely dark. Not the dark of interstellar space, where at least distant stars provide faint points of reference, but a darkness without even those. A universe full of matter and energy, quietly organizing itself under the force of gravity, producing no light whatsoever. Then, approximately 200 million years after the Big Bang, the first stars ignited. In the densest regions of gas, gravity had been winning its slow battle, pulling matter closer and closer together, until the pressure and temperature at the core of a collapsing cloud became sufficient to trigger nuclear fusion. Hydrogen nuclei began combining into helium, releasing energy as light and heat. The first stars were enormous, hundreds of times more massive than our Sun, and they burned with ferocious intensity, living only a few million years before destroying themselves in colossal explosions. But those explosions seeded space with heavier elements, the raw material for everything that came after. Rocky planets, water, carbon chemistry, eventually life. The universe has been getting progressively brighter since those first stars ignited, as more and more generations of stars formed and galaxies assembled themselves from smaller structures merging together under gravity. We live now in what might be called the golden age of cosmic illumination, an era when the universe contains more stars than at any previous time, when galaxies are numerous and relatively close together in cosmic terms, when the night sky displays a richness of structure that earlier epochs lacked. But this era has already passed its peak. Star formation reached its maximum rate approximately 10 billion years ago and has been declining since. We are living in the long, gradual afternoon of the universe's most luminous period. The future belongs to the darkness again. Stars will continue forming for trillions of years, but at decreasing rates as the available gas in galaxies gets consumed or expelled. The most massive stars will die first, collapsing into black holes or neutron stars. Medium-sized stars, like our Sun, will exhaust their hydrogen fuel after roughly 10 billion years of burning, swell into red giants, shed their outer layers, and collapse into white dwarfs, dense Earth-sized embers that cool over trillions of years into dark, cold objects called black dwarfs. Small red dwarf stars, far more numerous and far more frugal with their fuel, will burn steadily for tens of trillions of years, but even they will eventually exhaust themselves. In something like 100 trillion years, a number so large that the current age of the universe is a rounding error by comparison, the last star in the universe will burn out. What remains will be a collection of dead objects drifting apart in expanding darkness. Black holes, neutron stars, cooling white dwarfs, frozen planets orbiting dead stars, rocks and ice and dust clouds with nothing to warm them. Occasional collisions will produce brief flashes, a planet consumed by a black hole, two dead stars merging in a final explosion, but these events will grow rarer across timescales that make the current age of the universe look like a moment. The darkness will not be sudden, it will be a slow, patient, inevitable deepening. Even then, the process isn't finished. Quantum mechanics predicts that black holes themselves are not permanent. Stephen Hawking calculated that the extreme conditions near an event horizon should cause black holes to slowly radiate energy, losing mass over inconceivable timescales. A black hole with the mass of our Sun would take roughly 10 to the power of 67 years to evaporate, a number that requires 67 zeros after the 1, and which exceeds the current age of the universe by a factor that has no useful analogy. Supermassive black holes, millions or billions of times more massive, would take proportionately longer. But given sufficient time, and the universe will apparently have it, even they will be gone. The final state of the universe, trillions upon trillions of years from now, is a near-perfect void, a scattering of photons and neutrinos and other fundamental particles spread across space that has expanded to unimaginable size at a temperature approaching absolute zero, with nothing happening anywhere ever again. Physicists call this the heat death of the universe, maximum entropy, the state where no energy gradients exist to drive any process, where the laws of thermodynamics have finally collected on every debt. It is not dramatic. There is no explosion, no collapse, no final event, just a stillness that extends forever in all directions without variation. The darkness at the end of time makes the darkness of intergalactic space seem positively lively by comparison. We are extraordinarily fortunate, in a temporal sense, to exist when we do. The universe is currently at a stage where stars are numerous, where their light has had time to build up across the sky, where the distances between galaxies are still close enough to observe, where the expansion of space has not yet carried everything beyond our horizon. Future civilizations, if they exist billions of years from now, will inhabit a dramatically darker universe. The galaxies beyond our local group will have receded beyond the cosmic horizon, not merely too far to see clearly, but too far to see at all, moving away faster than light can cross the distance. those future astronomers, staring at a sky containing only their own galaxy and perhaps a few nearby companions, might not even realize the universe is expanding, because there will be nothing far enough away to observe the expansion. They will inherit a smaller, darker, quieter cosmos, and they will have no way of knowing what they have missed. When we look at the darkness of space, we are therefore looking at something that is simultaneously a property of this moment in cosmic history and a preview of what is to come. The darkness we see is neither as deep as the primordial dark ages before the first stars, nor as shallow as the blazing density of the early universe. It is the darkness of a universe in middle age, still rich with light, but already moving toward the cold conclusion that thermodynamics has been promising since the beginning. All of this is what the darkness tells us if we are willing to read it carefully. But reading it requires confronting a series of truths that don't sit comfortably alongside the intuitions built into us by millions of years of evolution on a brightly lit planet. Consider what the darkness means for the question of whether we are alone. If other intelligent civilizations exist anywhere in the universe, we might reasonably expect to see some sign of them. A civilization advanced enough to spread across its star system, let alone its galaxy, would presumably leave detectable traces, energy emissions, structured signals, the unmistakable geometry of engineered structures. We have been listening for radio signals from other civilizations since 1960, scanning the sky with increasingly sensitive instruments, and we have found nothing unambiguous. The darkness is unbroken by any obvious evidence of other minds. This silence sits at the heart of what physicist Enrico Fermi crystallized into a simple question during a lunchtime conversation in 1950. If intelligent life is common in a universe this old and this large, where is everybody? The universe has been producing stars for nearly 14 billion years. Many of those stars are older than our sun. Civilizations with that much of a head start could theoretically have spread across the galaxy many times over, given even modest assumptions about travel speed and colonization rate. The fact that we see no evidence of this is either telling us that intelligent life is extraordinarily rare, or that something consistently prevents civilizations from becoming visible across interstellar distances, or that they exist but are hidden from us in ways we don't yet understand. The darkness offers no answer to this question, only the question itself. It stares back at us, indifferent and uninformative. Perhaps we are genuinely alone, the first minds to arise in this galaxy, or one of only a handful. Perhaps others exist, but the distances are simply too vast, the signals too faint, the timing too improbable for contact. Perhaps the universe is populated with islands of consciousness separated by darkness so profound that no bridge between them is possible. Any of these possibilities has profound consequences for how we understand ourselves, but the darkness will not tell us which is true. It keeps all possibilities open while confirming none of them. What the darkness does do, reliably and unavoidably, is produce a particular effect on human beings who confront it directly. Not the comfortable, familiar darkness of a bedroom at night, but the real thing, the darkness that astronauts encounter when they work in shadow during a spacewalk, when they float in the hull of a spacecraft in interstellar simulation, when they look out a window away from the Earth and the Sun into the void that extends for trillions of miles before it reaches anything. The effect is not easy to describe, which is why astronauts struggle with the language when they try. It isn't simply frightening, though there is often fear involved. It's more like a confrontation with something your cognitive architecture was never designed to process. Your brain evolved to handle the darkness of a forest at night, the darkness of a cave, the darkness of a moonless sky. Environments where darkness meant danger, where predators might be concealed, where getting lost was a real possibility. That darkness was always a temporary condition with a known solution: fire, shelter, dawn. The darkness of deep space has no solution. It doesn't end when morning comes. It doesn't end at all. It simply continues in every direction without variation for distances that no human mind can genuinely hold. The psychological research on prolonged darkness is instructive. Studies of people placed in completely lightless environments, sensory deprivation chambers, deep cave experiments, isolation protocols, consistently show a progression from initial relaxation to a more disturbing state. Without visual input, the brain doesn't go quiet. The visual cortex, denied its normal stream of data, begins generating its own. Hallucinations emerge, geometric patterns at first, then more complex imagery, sometimes entire scenes with narrative structure. The brain is not malfunctioning. It is doing exactly what it evolved to do, which is process visual information, applied to a context where there is no visual information to process. It invents what it cannot find.
In genuinely prolonged darkness, the brain begins reorganizing itself. Within days, the visual cortex starts responding to other senses. Sound begins activating regions that would normally process sight. Touch begins triggering visual processing areas. This is called cross-modal plasticity, and it happens faster than researchers initially expected. The brain is plastic enough to reassign real estate that usually belongs to vision if vision stops contributing information. Return to normal lighting conditions after extended time in darkness, and the readjustment is disorienting. The brain has to reclaim territory it had already begun repurposing. Astronauts working in shadow during spacewalks don't spend enough time in darkness for this kind of reorganization to begin, but they do report a primal response that bypasses rational thought entirely. The knowledge that you are safe, tethered, equipped with lights and communication does nothing to prevent the instinctive alarm that fires when complete darkness surrounds you. The fear is not a conclusion your mind reaches after considering the evidence. It is something older, a signal from systems in your nervous system that predate language and reason by hundreds of millions of years, systems that recognize the complete absence of visual input as a categorical emergency. Those systems do not update their threat assessment based on the fact that you happen to be on a spacewalk rather than on a savanna. Complete darkness is complete darkness, and every animal that walked or swam or crawled has spent its evolutionary history treating complete darkness as a situation requiring urgent action. In space, that urgency has nowhere to go. There are no predators. There is nothing hiding in the shadow. There is only the shadow itself, permanent and boundless, and you floating in it with a set of emergency responses firing in your nervous system that have no target and no resolution. Some astronauts describe a secondary effect that emerges after the initial fear response, a kind of existential vertigo, a sudden and visceral understanding of scale that intellectual knowledge about the size of the universe had never provided. You can know that space is vast. You can know the numbers, the distances in light years, the counts of galaxies, the age of the cosmos in billions of years. You can understand them mathematically and discuss them fluently. But floating in shadow, looking out at darkness that genuinely extends for trillions of miles before reaching anything, you feel the vastness in a different register, not as information, but as experience. The feeling has been compared to standing at the edge of a cliff, where the intellectual knowledge that you could fall produces a physical response in your body, but intensified and without any solid ground beneath you. The void is not below you, it is everywhere. The Apollo 8 mission of December 1968 was humanity's first direct encounter with this experience at a distance from Earth. Frank Borman, James Lovell, and William Anders became the first humans to leave Earth orbit entirely, traveling to the Moon on a journey that took them farther than any other human being than anyone had ever been. When their spacecraft passed behind the Moon on Christmas Eve, radio contact with Earth was lost. For approximately 45 minutes, they could not communicate with anyone. They could not see the Earth. They orbited a dead, cratered world in silence, looking out at a darkness that had no reference points except distant stars. James Lovell described looking out into that darkness and feeling a loneliness that the word alone cannot contain. Not the ordinary loneliness of being physically separated from people you know, but something more fundamental, a recognition that the nearest other human consciousness was a distance away that the mind genuinely could not hold. The darkness wasn't simply around them, it was demonstrating something. Every direction he looked, except toward the lunar surface below and the sun to one side, was pure void. When they emerged from behind the Moon and Earth rose above the lunar horizon, the emotional relief among the crew was described as overwhelming. The small blue and white sphere, half illuminated against the blackness of space, was home in a sense that transcended sentiment. It was the only complex object in a universe of simplicity, the only color in a monochrome field, proof that somewhere in the darkness something warm and alive and known existed. William Anders reached for his camera and took what became one of the most reproduced photographs in human history, Earthrise. The image shows our planet rising above the gray lunar horizon, floating in absolute blackness, fragile and brilliant and impossibly alone. The power of that photograph comes precisely from the darkness surrounding it. Without the black of space to frame it, Earth would be just a surface. With the darkness, it becomes something else, a declaration that life exists here and nowhere else in the visible frame,
that this small sphere is the entirety of everything we know and everyone we have ever known, suspended in a void whose scale the image communicates directly. People who saw that image in December of 1968 reported that it changed something in their understanding of the world, not intellectually, but emotionally. The fragility of Earth was suddenly not an abstract concern, but a felt reality. The darkness made it true in a way that words and numbers had not.
Apollo 13, 2 years later, provided a different and darker encounter with the void. An oxygen tank explosion crippled the spacecraft on its way to the Moon, forcing the crew to abandon the command module and shelter in the much smaller lunar module. To save the electrical power they would need to get home, nearly all non-essential systems were shut down. The interior of the spacecraft went cold and dark. The crew floated in near blackness in a vessel with uncertain life support, surrounded by space that they now understood was not merely the backdrop to their mission, but the actual hostile environment they were trying to survive. James Lovell wrote later about looking out the window during those long, uncertain hours and noticing something about the darkness that he hadn't registered before. Its complete indifference. It wasn't menacing. It didn't want them to die. It didn't want anything. It simply was, unchanged and permanent, as unconcerned with the question of whether 3 human beings survived as it had been before they arrived and would be after they were gone. He found this quality more unsettling in its way than active hostility would have been. An enemy can be reasoned with, or fought, or outwitted. The indifference of the void offered nothing to push against. It simply continued being itself, while their survival remained uncertain.
They made it home. The mathematics of orbital mechanics and the problem-solving of flight controllers on the ground brought the damaged spacecraft back through re-entry and into the Pacific Ocean. The darkness waited and watched and cared about none of it. Our robotic emissaries have traveled farther into that darkness than any human. The Voyager spacecraft, launched in 1977 to take advantage of a rare alignment of the outer planets that occurs only once every 175 years, swung past Jupiter, Saturn, Uranus, and Neptune before continuing outward. Voyager 1 crossed the boundary between the solar wind and interstellar space in August of 2012, becoming the first human-made object to enter the space between the stars. It is currently more than 23 billion kilometers from the Sun. Radio signals traveling at the speed of light take more than 22 hours to reach it, and the same to return. The Sun, from Voyager's position, is still the brightest object in the sky, but only the brightest point of light, nothing more. Earth is completely invisible. The spacecraft is still transmitting, though its power, supplied by the radioactive decay of plutonium, decreases by about 4 watts per year. Within the next few years, it will no longer have enough power to operate any of its instruments. It will fall silent, and it will continue traveling through interstellar space in the dark, carrying a golden record containing sounds and images from Earth, music, greetings in dozens of languages, the sounds of wind and rain and surf, photographs of human beings and their works and their world.
A message cast into the cosmic ocean. In approximately 40,000 years, it will pass within about 1.5 light years of a dim red star called Gliese 445. Not close enough to be captured, not close enough to be detected by any civilization that might orbit that star. It will continue past and keep going, a dark and silent artifact of human civilization, traveling through the dark and silent universe, perhaps forever. If the darkness of space tells us anything useful about how to live, it may be this: we are the light. Not metaphorically, literally. In a universe whose default state is cold and dark and empty, every source of warmth and illumination is precious because it exists against an overwhelming background of its absence. Stars are rare. Planets capable of supporting life appear to be rarer still. The conditions that produced human consciousness, the right star, the right distance, the right chemistry, the right sequence of geological and biological accidents across 4 billion years represent a concentration of improbable events whose magnitude is difficult to overstate.
The darkness doesn't diminish us. It contextualizes us. We are not small because the universe is large. We are remarkable because the universe is mostly nothing. And here on this particular rock, orbiting this particular star, something happened. Matter became organized enough to look back at the void and wonder about it. Atoms assembled themselves into structures capable of asking why the sky is dark. That is not a trivial achievement measured against the background of a universe that spent most of its history producing nothing but hydrogen clouds drifting through cold darkness. As we begin, tentatively and carefully, to extend ourselves into that darkness with spacecraft and probes, and eventually, if we survive long enough, with human beings living beyond Earth, we will carry the light with us. Not just physically, in the LED arrays and habitat lighting of our spacecraft and settlements, but in the more important sense, the light of awareness, of curiosity, of the particular and apparently unique phenomenon of consciousness trying to understand its context. The darkness existed for billions of years before we arose to observe it. It will exist for trillions of years after our sun burns out. In between, briefly and contingently and against all odds, something in the darkness learned to see.
That strikes me as worth noting. The universe, left to itself, produces darkness. We produce the other thing. Whatever meaning the cosmos has, and the darkness suggests it has none inherent, none built in, none guaranteed, we are apparently what meaning looks like when it manages to exist anyway, in the narrow gap between the darkness before and the darkness after. The night is not empty. It is full of everything the universe has spent 14 billion years producing. Most of it is dark. Some of it, here, briefly, is not.